Okay, well, I'll let you look through these answers first for a few seconds, and then we'll start the next one. You can pause it to look at them if you want to. So this was a linear exponent, so we didn't have to do substitution rule. I just divided by 3. Same here, that was linear, so divided by -2. I did this one out just in the usual way. Here you call u the cos. The derivative of cos is minus sine, and there is a sign there, so that will work. Here the exponent is x squared plus x. The derivative of that is 2x plus 1, and there happened to be a 2x plus 1 in front. Okay, so there's your answers. Okay, the next type is trig with arguments other than x. So they work the same way as the exponential. Okay, so trig with the argument other than x. So again, the linear ones, those should be very straightforward. Let's just write down the trig integrals that we know. Before we start. I'm just writing these pairs beside each other because they are easier to remember in pairs like that. The sine and the cos, the secant squared and the cosecant squared, the secant tan and the cosecant tan. And then the other memorized ones that aren't ones that we had from derivatives are the integral of secant is ln of secant plus tan. The integral of cosecant is ln of cosecant minus cotan. So they're similar, but this one has a negative. And it actually is because the cosecant gives us a negative. So it does change it in that way. Tan, I've been putting theta, so we'll put a theta, is the ln of secant. We could actually, and took cotan first. So there's a lot of trig ones. And we could add in the hyperbolic trig while we're at it, because these will work the exact same way. I don't know if I put x, but... And the hyperbolic cosine is sine. Those are both positive. All right, this is the argument. The h is part of the symbol. Okay, so all of these, you would really need to memorize them. So you should practice writing them because you do need to know them. Okay, so all of these will work the same with our examples. So, first, if the argument is linear. Then the answer is here, but we divide by the derivative of it. So, for example, if we had sine of 2x Then the integral sign is negative cos, so this would be negative cos 2x divided by 2. Instead of dividing by 2, you could put it as a half out front. Not necessary, but you could do it that way. So, for example, if we had secant 5x tan 5x, this whole thing is one integral. So then our answer is still 1. It's secant of 5x. And we divide by the derivative of 5x, which is 5. Okay, and we can put in, say, if we had tan of 2x plus 1, the integral of tan is ln of secant. So we would say ln of secant of 2x plus 1, rewrite the argument, but divide by the derivative of that 2. But that's the whole thing divided by 2. Or you could put 1/2, which probably would look better here, but really, as long as you made sure that you indicated it was over the whole thing, not just the secant, it would be okay. Okay, so that's if the argument's linear, so any of those would apply. If the argument is not linear, then the derivative of it has to be in front. So for example, if we had some trig with an argument here, the derivative of the argument would have to be out front. So for example, if I had x squared cos of x cubed, this would apply. The derivative of x cubed is 3x squared, and there's an x squared out front. So we would let u be x cubed, the argument. The derivative is 3x squared. There's an x squared. So rearrange this. And we rewrite the cos first. We called this u. Drop these off, and in their place, du over 3. To move that 1/3 out front. Don't have a lot of room here, but derivative of cos is positive sine, so sine u plus c, and u is x cubed. And there would be your answer. So it kind of works the same. It's just that these ones, same as the exponential, but these ones look a little bit more confusing because there's so many different integrals that I could write down. So I'm going to write a few of these, and we'll try them. I want to sort of keep going back to this list to see what the actual integral is. So I'll just put it up here, and we'll pull it back down when we need it. Okay, so a couple examples. A lot of times you'll see something like this. So there's a secant squared of e to the x. We would call it the argument is the part we're calling u. That's this part. The derivative of that is also e to the x, and that's why there's another e to the x out front, because the derivative also has an e to the x. If we rearrange that, e to the x dx, that's what we will drop off. So write it, ignoring the stuff we've underlined, because that's going to be replaced with the du. Write the secant first, so secant squared, u. These drop off, and in their place du. Integral of secant squared, it's right at the top here, tan, and it's a u plus c, and then we just write the u back in. You could put brackets for the argument if you prefer. Okay, so this next one. So the argument doesn't have a bracket here, but it's understood to be x squared, so we'll call that x squared. Derivative is 2x. So look back at what else is left. So we called that u. What else is left is an x and a dx. Can we rearrange this to have an x and a dx? Yes. So replace it. Oops, secant, write that first with the u. Drop these off, and in their place, du over 2. Bring that 1/2 out front. And the integral of secant, see if we can get it up here. There it is, the top of the page. Whoops. Right there. So 1/2, this would be ln of secant u plus tan u plus c, and then replace the u. U is x squared. Okay. I've got one that people find a bit tricky. Let's do hyperbolic. Okay, so a little bit tricky because we've got a fraction here, but a fraction is okay. What I would probably do is, this is attached, remember, this is hyperbolic sine of root x. So you would take this as the trig type, so we're going to call u this root x. And you notice there's another root x here, but that's really important, because if we have a root x and we take the derivative of that, (1/2) x to the minus 1/2, taking the derivative, subtract 1 from the exponent. Now, if you look out here, let's rewrite it. This happens with square roots all the time. This is actually 1 over root x dx. Do you agree? See, this is the hyperbolic sine. And if we break it up, this would be 1 over root x dx. Okay, so looking at that as two fractions. Now look over here. Let's just get rid of the negative exponent, and we do have a 1 over root x. So what we've got here is a 1 over root x and a dx, and you need the fraction. You can't put u on the bottom of the fraction there, because we won't get rid of this. This is 1 over root x dx when we cross multiply. And actually, when we cross multiply that 1/2, this 2 would go up to the top. And then we have a 1 over root x, and the dx goes up. And that's exactly what we were looking for, 1 over root x dx. Write the hyperbolic line first. We called that u. This whole thing comes off, and it's 2 du. Move the 2 out front. The integral of the hyperbolic sine is the hyperbolic cos. And u was equal to root x. You could put a bracket around there if you like. Okay, so with square roots, that's really tricky. There it is. The square root is 1 over the square root when you take the derivative, so you need to have a square root and a 1 over square root in the question for that to work. We'll do more of these after, but that's the basic idea. Okay, so I'll put a couple for you to try. Okay. Trying to keep the videos to about 15 minutes. or less. Okay, so trig for you to try. There's lots of trig ones to try. I'll just leave a little room. Let's try one of those square root. So the argument is a square root, and then it has a 1 over square root in it for it to work. Okay, so here's 4 for you to try, and I'll have the answers at the start of the next video.